At the beginning of the Industrial Revolution, most of the manufacturing world was powered directly by water. Any industry needing power had to be located along the banks of a river or stream, or the course of the river had to be diverted to reach the plant. It was the Welsh who first employed steam power in industry to operate the great mine pumps that lifted standing water from working mines. Steam soon became the world's most popular power source, chiefly because it could be produced cheaply and transported easily to one or several workstations. Steam has provided power to drive engines, turn turbines, heat or cook products, and more. Today, in fact, steam is used in at least one stage of the process or manufacture of almost every product we use. In order to perform all this work, however, the steam must release its heat to the product or work surface. When it gives up its heat, the steam condenses or reverts to water. If this condensate is not removed, not only does it form a barrier between the steam and the work surface, but it also reduces the heat transfer area. Initially, condensate was removed by simply cracking a valve, wasting the hot condensate and some steam as well to the atmosphere. The next step in condensate removal was the application of an orifice plate. These plates were simply discs drilled with a fixed hole or orifice. They were inserted at the steam line drip point or equipment discharge line, draining condensate and venting non-condensables from the steam space. The orifice plate had its problems, though. The small opening was easily blocked by dirt. The orifice plate was simply a fixed hole. It had no way of responding to changes in pressures or condensate load, and the wet steam discharge eroded the orifice. Over the years, many devices for removing condensate from steam by responding to changes in the system have been tried and laid aside, but each has been based upon one of a few simple principles of operation. The first is that steam, a gas, is lighter than condensate, a liquid. This difference in density is usually detected mechanically with some type of float. Another principle states that for any gas there is a temperature, called the saturation temperature, below which the gas is condensed. Traps based on this thermostatic principle use a temperature sensing element to control trap operation. The third is the thermodynamic principle, under which energy is transferred whenever liquid changes into a gaseous state. At the instant a molecule of water boils at atmospheric pressure, it expands about 1,600 times. In a confined space, this results in pressure and velocity changes. Traps that work on the thermodynamic principle are controlled by these changes. A look at present traps designed around these principles will show how they respond to various steam system characteristics. Let's start with mechanical traps, those that respond directly to the density difference between steam and condensate. The IB steam trap is a continuous drainage, intermittent discharge device that operates on the mechanical principle. The heart of the inverted bucket trap is this bucket. In the inverted position, it acts as an open float. It is capable of functioning under very high pressures because the same operating pressure is exerted both inside and outside the bucket. A small orifice called a bucket vent is located at the top of the bucket to ensure that non-condensable gases cannot be trapped inside the bucket. Steam, air, and condensate enter the trap through an inlet tube beneath the bucket. Air and condensate are discharged through an orifice at the top of the trap. At the orifice is a valve that is linked by a lever to the top of the bucket so that the valve is closed when the bucket is in the up position. The body of the trap is a cylinder which contains the bucket. During proper operation, this cylinder is always filled with condensate to a level above the top of the bucket. This condensate provides a constant water seal above and around the bucket, preventing live steam from escaping from under the bucket. Finally, in the cap of the body is a space above the water seal where any non-condensable gases which have passed through the bucket vent will collect while the valve is closed. Incoming steam is trapped between the top of the bucket and the water seal below. When approximately 2/3 of the volume of the bucket is filled with steam, the bucket becomes buoyant and floats to a point where the valve is pushed toward the orifice by the bucket clip extension. The higher condensate velocity near the orifice propels the valve into the seat, where it is sealed and held shut by differential pressure. Radiation causes the steam inside the bucket to cool and condense. If the condensed steam is replaced by more steam, the bucket remains buoyant and the valve closed. However, when enough steam has been condensed by radiation and is displaced by entering condensate so that only 1/3 of the bucket volume contains steam, the bucket loses buoyancy. As more steam condenses, the bucket becomes heavy enough to pull the valve off its seat. With the discharge valve open, condensate flows down around the bottom of the bucket and out through the discharge port. Air too rises to the top of the bucket, where it flows through the bucket vent and water seal, accumulating at the top of the trap. When the valve opens, the air is pushed out of the trap ahead of the condensate. The automatic differential condensate controller is a unique drainage device that is able to vent large amounts of flash steam and non-condensables. It may also be used wherever a live steam purge is needed to scrub the system. The DC operates under the same principles as the inverted bucket steam trap and is constructed similarly. The important difference is a secondary discharge tube which runs from the center of an umbrella-shaped shield coaxially through the inlet tube and is metered by a manual valve at its outlet. The incoming condensate and gases are prevented from directly entering this secondary discharge by the shield. The condensate forms a seal, trapping the gases inside the bucket, as with the IB. Steam, flash steam, and any non-condensables rise around the shield to the top of the bucket. The manual metering valve is adjusted to remove these gases during full capacity operation or to meet the velocity requirements for purging the system. The DC may be piped in one of two configurations depending on the job requirements. For secondary steam recovery, the discharge of the metering valve is piped to a separator and then to the top of a secondary steam header and transported to other workstations. If the flash steam and non-condensables are to be removed but not used in a secondary steam system, pipe the discharge of the manual metering valve directly to the condensate return line. At startup, steam, condensate, and air enter the inlet tube beneath the bucket. With the IB valve wide open, air is discharged through both outlet ports. Condensate fills the trap and drains through the main discharge port until enough steam collects under the bucket to float it, closing the main valve. The discharge of condensate is controlled by the position of the bucket, as with the IB trap. The manual metering valve controls the discharge of steam, flash steam, and air from the secondary outlet. Float and thermostatic traps offer a combination of mechanical and thermostatic operation. A closed float is used to sense the density difference between a gas and a liquid. The float is attached to one end of a lever which pivots inside the trap. At the opposite end of this lever is a valve that is seated when the float is at rest. Condensate enters through the inlet near the top of the trap and raises the float, opening the valve. The condensate drains from the trap through the outlet near the bottom, leaving a condensate seal between the inlet and the valve. Above this seal, near the top of the trap, is a thermostatic bellows. The bellows responds to temperature change. When this space is filled with hot steam, the thermostatic valve is closed. Non-condensables, such as air, mix with the steam and cool the space near the top of the trap. When the bellows element cools sufficiently, the thermostatic valve will open and vent these gases into a passage leading to the trap discharge. At startup, the float is down, the float valve closed, and the thermostatic valve wide open. Non-condensable gases reaching the trap are immediately vented through the thermostatic valve at the top of the trap. Condensate collects at the bottom of the trap until the float begins to rise, opening the float valve. The float valve normally drains continuously from this point. The condensate level in the trap lowers and raises the float height, thus modulating the discharge flow. When steam reaches the trap, it collects above the condensate level and heats the thermostatic element, closing its valve. Hereafter, the thermostatic valve will open intermittently to vent mixtures of non-condensables and steam. Should the trap become waterlogged, cooled condensate would open this valve and drain to the discharge line. Thermostatic traps are opened and closed by temperature changes of the liquids and gases inside them. One type of thermostatic steam trap is the bellows trap, named for the accordion-like cylinder that operates the valve. The bellows contains a liquid charge which vaporizes at or slightly below the boiling point of water. One end of the bellows is secured within the body of the trap. The valve is located at the opposite end of the bellows. When the bellows charge vaporizes, the pressure inside the bellows increases. A sufficient increase in this pressure expands the bellows to seat the valve. There are two methods of constructing a bellows trap, which determine, among other things, how the trap will fail, open or closed. In both methods, the liquid charge is added and then a vacuum is drawn in the bellows, compressing it to an internal stop. Only water is used as the bellows charge of the trap which will fail closed, and the valve is positioned to seat just short of the bellows free length. If the bellows ruptures, it returns toward its free length and the trap is closed. In traps that will fail open, a mixture of alcohol and water is commonly used as a charge because it will boil just before the saturation temperature of steam is reached. At any temperature above this point, the internal pressure of the bellows will be higher than the system pressure. With this higher internal pressure guaranteed, the valve seat for these fail-open traps is placed so that the bellows extends slightly beyond its free length to seat the valve. If the bellows is ruptured, it returns to its free length and the valve opens slightly. In either case, on startup, the valve is wide open. Any water or air in the system can drain freely through the trap. As the system reaches operating temperature, hot condensate and steam enter the trap. The bellows element is heated until its charge vaporizes. When the resulting expansion raises the pressure in the bellows sufficiently, it extends, pushing the valve into the seat. With the valve closed, there is no flow through the trap. As the condensate in the trap cools, it steals heat from the thermostatic element. Eventually, this condenses the gas inside the bellows, lowering its internal pressure. The relatively higher system pressure outside the bellows compresses it and pulls the valve off the seat to open the trap. When the fluids and gases inside the trap reach sufficient temperature, the trap once again closes. Air and other non-condensables mixed with the steam also lower the temperature inside the trap. When the surrounding temperature falls below the saturation point of steam, the charge begins to condense. With greater pressure outside than inside the bellows, it compresses, pulling the valve off the seat. The disc trap is a thermodynamic trap. These traps are operated by the energy released when the condensate changes state, or flashes between the disc and the seat. The disc trap contains only one moving part, the controlled disc itself. When the trap is closed, the disc is on the seat, sealing both the inlet and the outlet orifices. The area containing the disc is called the control chamber. It is a relatively large volume space with restricted inlet and outlet ports. It is the change of state which occurs here that normally controls the opening and closing of the disc trap. On startup, condensate at the inlet port pushes the disc off the seat and flows freely to the outlet port. Condensate passing into the trap drops in pressure. If the condensate temperature is sufficiently high to have reached the saturation for this reduced pressure, some of the condensate re-evaporates or flashes back into steam. Since steam occupies a much greater volume than condensate, flow velocity increases between the disc and seat, resulting in a pressure reduction in this area. At the same time, steam and some condensate collects on the side of the disc opposite the seat, and pressure here rises. The resulting differential pressure across the disc creates a force which snaps the disc onto the seat. The steam in the control chamber pushes on the total area of the disc, while the inlet and back pressures affect only the smaller areas of the inlet port and the discharge groove. This imbalance of force holds the trap shut. Heat radiating from the bonnet causes condensing in the control chamber, reducing the pressure above the disc. When the force above the disc is overcome by the forces below it, the disc is pushed off the seat, opening the trap and starting the next cycle. Since any gas, including air, causes the trap to close, some provision must be made to remove non-condensables from the control chamber. This is usually accomplished with a rough grind applied to the seating side of the disc, or a bleed passage machined between the control chamber and the outlet. In an ideal environment, all of these traps might function equally well. They all have the facility to trap steam and remove condensate. Unfortunately, no steam trap operates in an ideal environment. Friction, corrosion, and erosion are all detrimental to the trap's ability to conserve live steam. The operating principles themselves will determine how fast the trap responds to changing condensate loads and how well the trap seals under non-ideal or intermittent conditions. The standards and materials used in manufacturing the trap also affect its service life. Steam systems themselves are dynamic. They are turned on and off, subjected to varying load demands, use water of questionable and varying purity, and often operate in freezing temperatures. Therefore, there are a number of operating conditions that must be considered in evaluating a steam trap's performance for any particular job. For each condition, we will rate the trap in one of three ways. Green indicates that the trap performs well and is recommended under the condition outlined. Red indicates that the trap is highly susceptible to problems if operated under the stated condition and is not recommended. Yellow means that caution should be applied in using a particular trap if the condition exists. The trap may operate marginally under one condition, but perform so well under another that its use is acceptable with an increased PM schedule or if protective devices are installed. One of the first evaluations should concern the amount of live steam lost through the trap when it's new. All trap types condense some steam due to thermal radiation, but live steam is discharged from some types even when new because of the way they are controlled or sealed. The water seal prevents live steam loss through the IB and the primary orifice of the DC. Disc and bellows traps prevent live steam loss by closing in the presence of steam or condensate near steam temperature. F&T and DC traps pass live steam mixed with any air they vent. While this loss is greater than with other traps, it is generally considered acceptable in applications which require the venting of large air accumulations. Production rates, ambient temperature, and steam quality are just a few of the factors which vary the condensate load to the trap. The operating principles of each type trap determine the nature of its response to varying condensate loads. The mechanical traps, the IB, DC, and F&T, are continuous drainers. They are controlled directly by the amount of condensate entering their bodies and therefore respond immediately to any load changes. Thermostatic and thermodynamic traps react to changes of temperature or changes of state rather than responding directly to the presence of condensate. All traps are required from time to time to handle the heavy air and condensate loads of startup. At startup, the system is cold, devoid of steam, and often has large accumulations of condensate and air in the lines. F&T and bellows traps are most recommended for frequent startup conditions because of their ability to handle large air loads. The F&T and bellows traps are wide open at startup and remain open until the system nears operating temperature. The manual metering valve of the DC provides a controlled bleed for startup air loads. The small bucket vent of the IB trap is sized to prevent live steam loss, but may cause temporary air binding during startup. The addition of a thermic vent to an IB passes large startup air loads, but closes to conserve energy when the system reaches operating temperature. The disc trap closes when any gas, including air, moves across the bottom of the disc. The air trapped above the disc does not condense and takes time to bleed off. In a situation with frequent startup or heavy air loads, disc traps are not recommended because they take too long to evacuate the system of non-condensables. Back pressure is the pressure in the condensate line which opposes the supply pressure. It is created by such things as pipe friction, flash steam, differential valves, or receiver relief valve settings, and elevated condensate return lines. For every 2 feet of condensate elevation, approximately 1 pound of back pressure is created. Back pressure reduces the differential pressure across the trap. Since the differential pressure across the trap provides the force for drainage when the trap is open, the best any type of trap can do is operate at a reduced capacity when the back pressure is increased. An increase in back pressure to a disc trap increases its cycle rate. If the cycles become fast enough, the trap may reach a point where it machine guns. Back pressure may increase to the point where the trap remains open, blowing live steam. Where high or fluctuating back pressure occurs, the disc trap is not recommended. Steam traps must be sized to handle the heaviest loads they might encounter. When production is down or demands on the system are low because of the season, traps may be subjected to loads far below their design limits. The trap must continue to discharge condensate as it is formed and trap live steam in the system even under these low load conditions. The IB and DC compensate for low load situations by operating in a condition known as dribbling. Whenever the valve cracks open, condensate flashes across the valve seat. Because of the volume and velocity increases that accompany this flashing, there is a sudden pressure drop in the orifice throat, resulting in an increase in differential pressure across the valve. If the entering condensate flow doesn't provide a sufficient water level under the bucket to counteract these increased closing forces, the valve snaps shut. F&T and bellows steam traps have modulating outputs at very low loads. In these traps, the opening and closing forces tend to balance out as the load decreases and the trap doesn't fully open or close, but modulates with the condensate flow. The disc trap is not recommended in situations where the average load is less than 3% of the trap's rated capacity. Live steam causes the trap to cycle frequently, prematurely wearing the seating surfaces. As condensate flows through the system, it picks up dirt and scale formed on the walls of the piping, as well as any solids that carry over from the boiler. Traps must be able to operate in the presence of this dirt without damage to or blockage of their orifices or mechanisms. The intermittent discharge of IB and DC traps create a self-scrubbing effect at the bottom of the trap. Dirt particles smaller than the orifice diameter are flushed from the system. With the orifice located at the top, dirt, scale, and other matter settling to the bottom of the trap will not plug the discharge port. The bellows trap may be oriented in any direction. When the valve is located at the top, this trap also resists clogging. Since the trap modulates on low loads, however, care must be taken that dirt large enough to lodge in the throttled opening doesn't enter the trap. The bellows trap in any other orientation and the F&T trap have valves in or near the bottom where dirt can accumulate, blocking the orifice. In addition, the small openings, when these traps modulate, are easily blocked open or closed by small dirt particles. The disc trap cannot be recommended in the presence of dirt either, because it has two sealing surfaces, both of which must be perfectly flat. The intrusion of dirt between the disc and seat not only provides a poor seal, but also aids erosion of the seat and disc surfaces because of the high velocity flow between them. The installation of a strainer immediately upstream of any trap will protect it, provided the strainer is properly maintained. Carbon dioxide is the primary non-condensable found in steam systems. Condensate and carbon dioxide coexist when temperatures in the system are at saturation. When the temperature drops below saturation, however, the two combine to form carbonic acid. This acid is extremely corrosive and will eventually eat through piping and equipment. Oxygen is another gas trapped in steam systems which speeds up corrosion. Not only should a steam trap operate in the presence of non-condensables, but it should also discharge them at or near steam temperature to prevent the formation of corrosives. The bucket vent of the IB and DC traps pass non-condensables through the water seal, where they are vented at or near steam temperature during each trap discharge. The F&T traps air above the condensate seal and vents it through the thermostatic valve mixed with some live steam 15 to 20 degrees below saturation temperature. The disc and bellows traps can both back up condensate. Although this subcools the condensate and air mix, there may be advantages to some systems in using the sensible heat in the water that outweigh the risks of corrosion. Water hammer can be a very destructive force. Water, like steel, is incompressible. It doesn't give. Hydraulic, thermal, or differential shock can send 100-pound columns of water accelerating toward a trap with devastating results. Although well-designed systems minimize the occurrence and severity of water hammer, its effects on a trap's performance must be considered in many situations. Traps that are designed to resist these damaging forces are recommended where water hammer is likely. The disc trap has no parts which can fail from this sort of shock. The IB and DC traps use open floats with the same internal and external pressures, making these resistant to water hammer. The same cannot be said for bellows or F&T traps, however. The fixed internal pressures in the float and bellows elements make them likely to collapse when subjected to these pressures. One of the most common uses of steam is to heat a product or maintain its temperature in a freezing environment. In these applications, when the system is shut down or when pressure is lost for a period of time because of a line or component failure, condensate can be subjected to sub-freezing temperatures. Even with the best insulation and installation procedures, the ability of the trap to resist damage from freezing should be considered for this service. Freezing conditions require a trap to withstand abnormal pressures, the results of which are much the same as with water hammer. The IB, DC, and disc can withstand some freezing without trouble, with the addition that the stainless steel IBs can actually expand under severe conditions and still operate after they are thawed. The more delicate bellows elements and the float in the F&T can be crushed if they retain condensate in their bodies when temperatures drop below freezing. The final, and probably the most important requirement, is service life. The service life of a steam trap is the amount of time it operates efficiently, conserving steam and removing non-condensables and condensate from the system. The benefit of long service life is lower operating expense. Generally, savings are realized from reduced energy consumption, repair or replacement costs, and downtime for maintenance. Obviously, all of the other requirements we've spoken of contribute to the overall life of the trap, along with the materials chosen for the trap and the care taken in its design and assembly. Both the IB and DC have excellent service life. They have low initial steam loss and respond favorably under the conditions we've looked at. Although the DC discharges some live steam mixed with the air in order to purge non-condensables, it handles large air loads better than the IB. The F&T trap is most often used on modulating systems because it is a continuous drainer that handles startup air loads and light condensate loads well. It may have a good service life if caution is taken to prevent damage to the trap in systems where dirt, freezing, and water hammer are likely to occur. Bellows traps can also have a good service life provided they are protected against water hammer. They can be piped in any orientation and they have good startup characteristics. Bellows traps do back up condensate, however, and the increased corrosion and water hammer potential may be a problem. The service life of the disc trap is expected to be short. Under heavy loads, the disc trap backs up the condensate, and on light loads, the high velocities through the orifice, as well as the violent impact of the disc on the seat, make the trap especially susceptible to wear. There is a proper trap available for any steam system. By balancing the requirements of your product with the conditions in your system, you can determine the trap most suitable for your application. Following this selection with proper installation, inspection, and maintenance ensures long life and low operating costs. At Armstrong, we make a steam trap for every situation. Your Armstrong representative has other videotapes and additional training materials. He is always glad to help you by providing further information on selecting, installing, and maintaining your traps.